right, hello and welcome to lecture Thanksgiving week edition. Today we are going to be concluding our discussion of VSEPR theory, which is valence shell electron pair repulsion theory. This is what we began developing in last lecture. And it has allowed us to move from the flat two-dimensional depictions of molecules we see in Lewis structures and analyze those two-dimensional Lewis structures to determine the kind of three-dimensional structure of a molecule and kind of the shape and that it takes, the bond angles, etc. So anyways, we're going to continue this discussion today. As I said, conclude it, wrap it up, and then we will move on to hybridization. Emma, it is a happy Monday. Even though we don't really get any break, or at least in this class, Thanksgiving break is Thursday off, Friday off, and we're a Monday, Wednesday class. So even so, it's kind of a happy Monday. We know we're going to get a little bit of a break towards the end of the week, at least. All right, so on Wednesday in last lecture, we looked at the different electron groups, right, and the geometries that they take. And we made it from 2 electron groups around our central atom all the way up to 5. And so I'm going to jump right back in where we left off. So we were talking about, so we had the Lewis structure, we had electron groups. I mentioned that this is sometimes called electron domain. Then we had the number of lone pairs, followed by the molecular geometry. The electronic geometry comes next, followed by molecular geometry. So here, let me just slide this over. So we had the electronic geometry, which is the geometry made by all the electron groups. The molecular geometry, which is the shape made by only the atoms, not the lone pairs, followed by the three-dimensional representation and bond angle. Oops, that's a little... All right, so we have our electron groups, and our electron groups determine our electronic geometry. Our number of lone pairs determine our molecular geometry. All right, so we're going to now move into 6 electron groups, right? We looked at the when there's 2 electron groups, and that's a linear electronic geometry. 3 electron groups is a trigonal planar electronic geometry. 4 electron groups is a tetrahedral electronic geometry, and then 5 was the trigonal bi-pyramidal electronic geometry. And we're going to go all the way in now. This is the last number of electron groups that we'll look at in this class. We'll look at SH6, which looks like so. It's a sulfur that's hypervalent, right? It's violated the octet rule, but sulfur is allowed to because it has it's on the third period, so it can have more than 8 electrons around it. And here it has 6 hydrogens, no lone pairs. So our number of electron groups in play, we have 6. And we so whenever you have 6 groups around your central atom, the electronic geometry is called octahedral. Oops. Octahedral. All right. Now that might be weird. You might be like, wait a minute, why is 6 octa isn't octa 8? Well, the reason why 6 electron groups is octahedral is an octahedron, which is a geometric solid with 8 sides, has 6 vertices to it. And so that's the reason why 6 electron groups is octahedral. It's because there are 6 vertices in an octahedron. So that's the reason for that. Here we have 0 lone pairs, and we know that whenever we have 0 lone pairs, our molecular geometry is equal to our electronic geometry. All right, so now the question is, how do you draw an octahedron? How do you draw the octahedral geometry? And the answer is there's 2 ways to draw this thing. And I'm going to show you both ways. Either is perfectly correct. I don't know why I put a carbon in the center, because we are dealing with sulfur. So one way to draw an octahedron is, so you're going to have 6 pairs of bonds. Each are going to be 180 degrees, kind of like each will form a straight line. So you could start by drawing 2 up and down, followed by 1 wedge and a dash on one side, and then a wedge and a dash on the other. That's the first way to draw an octahedron. The second way to draw an octahedron is you can draw it like so. You can draw 4 bonds in the plane of the board, 1 wedged, and then directly across 1 dashed. And like I said, either one is 100% correct. So these would be 2 correct octahedral depictions of sulfur hexahydride. When we talk about our bond angles here, oh man, it's okay. I can fix it. Okay, when we talk about our bond angles here, we're talking about in an octahedron, we saw in the trigonal bipyramid that there were 2 different types of bond angles, right? There's the 120 and then the 90. The nice thing with the octahedron is we're back to all bond angles being equal. So it doesn't matter which 2 you look at. All of these bond angles are 90 degrees. They're just a straight up right angle, 90 degree bond angle. Now, for those of you who have experience playing D&D or other tabletop games, you may have an advantage here over the ones that have not. If you're wondering what shape an octahedron has, if you've ever rolled a D8, which is an 8-sided dice, that's an octahedron. So the shape of these molecules is like an 8-sided dice. It's what you throw for, I believe, damage with a rapier. And those dice are, this molecule is the same shape of those dice where you have an H on every kind of vertex of that shape. So if you've played D&D and you've thrown a D8, you've held an octahedron in your hand. If you haven't played D&D, you should go do it for chemistry class so you can visualize what an octahedron, octahedral geometry looks like. All right, so this is the octahedron with 0 lone pairs, but as we know, as we start introducing lone pairs, we're going to change, the molecular geometry will change and our bond angles will change as well. So let's take a look at what happens when we start adding lone pairs to these structures. All right. And here, hang on. The screen might get a little jank for just a second. I apologize. There we go. And then once more. I accidentally drew something in the wrong layer, so okay, now we're good. Good to go. Okay, let's look at what happens. Okay, yeah, there's the screen getting kind of janky. Let's look at what happens when we start adding in lone pairs. All right, and for our first example of an octahedron with a lone pair, we're going to look at antimony, pentahydride. That is SB, and then it's got 1, 2, 3, 4, 5. Here's a Lewis structure. Five hydrogens, but if you draw the Lewis structure for this guy, it will also, you'll notice it'll have a lone pair on it as well. All right, now the number of electron groups, it's the number of atoms on our central atom plus the number of lone pairs our central atom has. So we have 6 total electron groups with 1 lone pair. Now, every time you have 6 electron groups, your electronic geometry will be octahedral. All right, but the question remains, we'll figure out the molecular geometry in a moment, but once you know the electronic geometry, you can begin drawing your structure because every octahedron is the same. And I'm going to draw it like so. All right. Oh wait, we don't have sulfur, we have antimony here. There is antimony. Now, when it comes to adding lone pairs to your structure, you can put them anywhere, just like with tetrahedrons. All right, at least the first lone pair you can put anywhere. With the trigonal bipyramid, they always went equatorial, but there are no axial or equatorial positions on a octahedron, so your lone pair can go anywhere. I'm going to place mine here, and then you throw your H's everywhere else. All right, now that is the electronic geometry. The molecular geometry, we want to know what is the shape this molecule has, not including the lone pair. So I'm going to take my lone pair and just represent it as 2 dots around my central atom. And when you look at this, the shape that these atoms make is it kind of makes a shape like a pyramid, but unlike the trigonal pyramidal geometry that we saw before, the trigonal pyramidal had three vertices on its base. This has 4. So this is called a square pyramidal geometry. All right, so this geometry is square pyramidal. All right, and our bond angles here, again, we know that whenever you have a lone pair, it pinches your bond angles in, so our bond angles here will be slightly less than 90. Whoops, not 18. That's way less. That lone pair on our central atom will pinch them down by a couple degrees. So this is the square pyramidal geometry. 6 electron groups, 1 lone pair. All right. Now this is the second to last geometry we have to learn. The last one, the final one, is 2 lone pairs, and then that'll be it for VSEPR theory. So let's go ahead and take a look at what happens when you have 2 lone pairs in play. And for that, look at Xenon Tetraflouride. So if you draw the Lewis structure, actually draw the Lewis structure. You've got 4 fluorines on your central atom. Then you've got a couple lone pairs. 2 sets of lone pairs. All right, so the number of electron groups that we're dealing with, we have 6. And once you know the number of lone groups, you instantly know your electronic geometry. 6 electron groups is an octahedral. Electronic geometry, followed by, and once you know your electronic geometry, you can draw in your octahedron, because every octahedron is the same. Sorry, those are 2 ugly wedges. I'm going to redraw those. All right. Oh, and I missed all my lone pair dots on this little structure. Let me fix that. All right. Now, we know that our electronic geometry is octahedral. How does changing the number of lone pairs affect the molecular geometry? You'll recall with the previous example when we had 1 lone pair, I said it didn't matter where you put that first lone pair. You could put it anywhere you want to. The second lone pair, that's not the case. Where you put the first lone pair dictates where the second lone pair will go. All right? Because lone pairs create greater repulsion, they want to be as far away from other lone pairs as possible. So if you put your first lone pair here at this position, your second lone pair must go on the opposite side, as far away as it can go. All right? If you put your first lone pair here, your second lone pair has to go on the opposite side of the molecule. And if you put your first lone pair here, the second lone pair, again, goes on the opposite side. So even though it doesn't matter where you put your first lone pair, where you put your first lone pair determines where your second lone pair goes. So you kind of want to keep this little thing in mind when drawing the 3-dimensional representation of a square planar geometry. All right. Same story here. Actually, you know what I'm going to do? I'm going to draw this same type of picture, but with the other depiction of an octahedron, just so you know how to do a square planar geometry if you like drawing it the other way. So for example, so this is the other way to depict a square planar geometry. Oh, hang on. There we go. So you can also draw it like this. And the same rules still apply. If you put your first lone pair here, the second lone pair goes on the opposite side. If your first lone pair goes here, second lone pair goes there. If your first one goes here, the second goes there. All right, so with that in mind, let's go ahead and draw Xenon Tetraflouride. I'm actually going to draw it like this because I think it'll be easier to understand the molecular geometry. When we do it, I'm going to put my first lone pair here, which means that my second lone pair must go as far away as possible. All right, so now we load up the molecule with fluorines. All right, so let's figure out our molecular geometry. We're only interested in the shape the atoms make, so we're going to erase the lone pairs and just depict them as two dots on our central atom. Now, one thing you can see is every single bond between xenon and fluorine in this molecule is in the same plane. All right, they're all in a plane, and it kind of makes a square shape. So the molecular geometry here is square planar. All right, and our bond angles on this thing are actually a pure 90 degrees. Now, wait a minute, you might be thinking, I thought that every time you added a lone pair, it's going to pinch our bond angles down 2 degrees. Why is it a pure 90 degrees? And that is an excellent question. Let me show you. So I'm going to draw the alternate depiction. The alternate way to depict a octahedron. I'm going to put these lone pairs here and here. And just for completeness sake, I'm going to draw in all of my lone pairs on all of my fluorines. All right. Now, when we added one lone pair to our octahedron, it started pushing down, forcing all of those bonds to kind of pinch in and go lower, right? And that's why we had the 88-degree bond angle in the square pyramidal geometry. But you'll notice here, you've got a second lone pair, and it's on the other side. This lone pair is pushing from below on all of these fluorines. All right, it's pushing from the opposite side. And so because they're on opposite sides of the molecule, each pushing, one pushing from the top, the second pushing from the bottom, the result is no change, no distortion to the bond angle because they have the same strength. It's one lone pair pushing from opposite directions. That causes the bond angles to be nice, clean, 100, not 180, 90 degrees from each other. All right, so that is an interesting part about the square planar geometry is there's no bond angle distortion due to lone pairs. All right. So that is it for VSEPR. At this point in time, you have seen all of the geometries that you could be tested on. There are more out there, but these are the main ones. There's some weird ones that we're not going to talk about. If you're interested, take upper division inorganic chemistry classes. You'll see all the cool stuff. But for right now, for this class, those are all the geometries that we're going to look into. Now, for the exam, and several of you have emailed me about exam 4. I will be, I'm in the process of figuring out exactly when it's going to fall, so that information will be coming out later today. So keep your eyes peeled. So with respect to VSEPR geometries, on the exam, and there'll be more information as I get closer to writing the exam. But you can be given a Lewis structure, or I could also give you a chemical formula. Or one or the other. And then the things that I can ask, these are what you'll see in the problems. I can ask for the number of electron groups. I could ask for the molecular geometries. I could ask for the electronic geometry. I could ask for the bond angles. So these are really the things that I could ask for. I could also ask, this is not VSEPR, so I'm going to put this in a different color. I could totally ask for the hybridization as well, which we haven't talked about that yet, but that will show up on the on exam 4. And so if you're wondering, okay, how are we going to be put to the test? How are we going to be tested on this information? That is how. I'll either give you a Lewis structure or a molecular formula. If I give you a molecular formula, you'll have to draw your own Lewis structure. And then I can ask you to tell me the electron groups, the molecular geometry, electronic geometry, bond angle, or hybridization. So what you really want to do is I highly recommend hitting up the TRO homework for this and just getting a lot of reps in practicing assigning molecular geometries, electronic geometries, bond angles, and hybridization, because that's how you'll be tested. All right, so that is VSEPR theory. Now we're ready to move on. Nope. To this idea of hybridization. Hybridization is a part of what's known as valence bond theory. All right, and for those of you who are going to be taking organic chemistry in your future, this is probably, I would argue that this is the single most important thing you're going to learn in Gen Chem that will apply and that you'll use in organic chemistry. Resonance is another big one, resonance structures, although it'll get explained in more depth when you take organic chemistry, and so you'll kind of have a chance to relearn it. Hybridization should be explained as well, but it's usually reviewed briefly. This is one of those things that you'll be using day in, day out in the context of organic chemistry. Whoa. Sorry about that. My finger just flicked my screen, so that's why Photoshop went flying. So anyways, yes, if you're taking OChem, here's what I was going to say before I mess up the screen. Hybridization isn't really discussed in Chem 401, so in second semester Gen Chem, you're not going to talk about this at all. So you're going to, take this final, have Christmas break, next semester, take 401, have a summer off, and then start organic chemistry for those of you who are planning on it. And when you do, it'll be almost a year since you've talked about hybridization, and this is what they start with. So if you're going into OChem, this is the topic that you'll want to come back and review ahead of time so you can kind of hit the ground running in that course. All right. So let's talk about hybridization. Now, I'm actually going to start at the end with hybridization. I'm going to start with the conclusion and just give you a kind of a fast way of assigning hybridization before I talk about what it is, why it's important, where it comes from. And the reason why I'm going to kind of explain this in reverse or tell you how to assign hybridization and then talk about what hybridization is, the reason why I'm approaching it this way is because exercise 5, which is available, at least in my lab section right now, asks you to assign hybridization. And it's going to be a little while before we finish kind of explaining what it is. But I want to give you kind of the quick and fast guide to assigning hybridization so you can start working on that exercise with plenty of time to complete it. And if I waited to give you kind of the big picture thing, if I waited for that till the end, it would leave you more crunched with that exercise. So I'm going to give you the quick and dirty, this is how you do it now, and then we'll build up to the why, what is it, all that stuff. All right, but here is how you assign hybridization. So assigning hybridization, you assign an atom's hybridization based on the number of electron groups it has. All right, based on the number of electron groups it has. So here's how. So we've got our electron groups. And our hybridization. All right. If you have 2 electron groups around your central atom, basically, here's the simplest thought with hybridization. You're wanting to ask yourself to hold this number of electron groups, whether they're bonds or lone pairs, it doesn't matter. How many orbitals do you need to use to hold this number of electron groups? So if you're going to hold 2 electron groups, you need 2 orbitals to do so. All right, you need 2 orbitals to do so. And so the first orbital you use is always s, the second orbital p. So you're going to use one s and one p orbital to hold these 2 electron groups. If you have 3 electron groups, you're going to need 3 orbitals. So you're going to use one s and 2 p orbitals. So if you have 3 electron groups, you will have sp2 hybridization. All right. If you have 4 electron groups, you're going to use your s orbital and all 3 of your p orbitals. So that will be sp3 hybridized. If you have 5 electron groups, we're going to need 5 orbitals. The problem is we only have 3 p orbitals. So sp3d must be the hybridization. You have to bring in one of the d orbitals for this hybridization scheme. Finally, if you have 6 electron groups around your central atom, you'll need 6 orbitals. So that hybridization will be sp3d2. All right, that is the hybridization. The way you say this, for example, if you have 4 electron groups, you would say that this is sp3, oops, not tree, 3 hybridization or hybridized. So that's how you kind of pronounce that. You say sp3 hybridized, sp2 hybridized, sp hybridized, etc. All right, now, so with this chart right here, you can complete all of lab exercise 5. All right, with that, you can complete all of lab exercise 5. So I would get started on it on the sooner side rather than the later side. One last thing I want to say about hybridization before we start talking about it in depth is there's one important thing I want to stress. Something you should note. Bonds are never hybridized. All right. When we are talking about hybridization, we are not talking about bonds. We are only and always talking about atoms. Only individual atoms. I want to emphasize that. Only individual atoms hybridize. All right. So with that being said, let's start talking about what hybridization is, where it comes from, why we need it. All right. So we are going to start with sp3 hybridization. You'll notice, some of you may have noticed already, that we underwent a very subtle shift when we moved from talking about electron configurations to Lewis structures to VSEPR. Which, as I've already said, electron configurations are looking at the orbitals and the electronic structure, the structure of the electrons around an individual atom, right? So kind of small. Then we started talking about Lewis structures, whole molecules together, and then VSEPR, right? The shape that those molecules take. When we started talking about Lewis structures, and when we started talking about VSEPR theory, we stopped talking about orbitals. If you go back, look at the lectures, they're not mentioned once. We don't talk about p orbitals, s orbitals, d orbitals, etc. And we just start saying like, oh, the electrons around this molecule, okay, they're going to bond, complete your octet rules, all that stuff. But we stopped talking about specific individual orbitals. And there's a problem, all right? There's a problem. And from this problem gives birth to the concept of hybridization. All right, so here's the problem with VSEPR theory. So if I ask you to draw out CH4, right, methane, You can draw that Lewis structure, no problem, right? It's just carbon with 4 single bonds to 4 different H's. All right, and then if I asked you to draw a 3-dimensional representation, give me bond angles, all that stuff, you could, right? We've got 4 electron groups, 4, no lone pairs, so we have a tetrahedral geometry. Every tetrahedron is the same. We have 2 bonds in the plane of the board, or page, or screen, 1 wedge and 1 dash. All right, we got hydrogens in every position, and we have bond angles of 109 degrees. All right, bond angles of 109 degrees. Here's the catch. Let's think about the orbitals available to carbon. If you look at carbon, the atom, we could write an electron configuration for carbon, right? It would have a helium core. And the valence electrons, which are the electrons farthest from the nucleus, they are the electrons involved in bonding for carbon. The valence electrons are in the 2s subshell and the 2p subshell, right? That's the electron configuration. For carbon, it's helium, 2s2, 2p2. Now, let me ask you a question. What angles do these orbitals form? All right, what are the angles that we can make with these orbitals? Well, we have 2 subshells, right? The 2s and the 2p. And there are 4 orbitals between them in the 2s subshell. We have an s orbital, right? There's the s orbital. Let me label my axes. And then in the 2p subshell, we have 3 more orbitals. Space. There we go. Should get my last 3-dimensional axis room to breathe. That's a little long. So we've got our z axes, our y, and our x. All right, well, for the p subshell, there's pz. You'll remember half of it is shaded. Here's pz. There's py. And then there's px, which is popping out of the screen at you and then going back behind. And here. All right, there we go. So this is px. Now, if we go back to our original question, what angles do these orbitals form? Well, the s orbital doesn't have any direction, right? So it's just there. It's just sitting there a blob. The only ones that do have direction that we can look at are the p orbitals, and each one is oriented along an axis. And what do we know about axes? They're all right angles. They're 90 degrees from each other. So if the electrons, the valence electrons for carbon, the ones that it uses to make bonds, are being held in s orbitals and an s orbital and p orbitals, why aren't the bond angles all 90 degrees from each other? Now, we know on some level the reason has to be, well, electrons repel each other. They want to get as far away from each other as possible. Yes, true. But let's put a finer point to it. What orbitals are they in? Because they can't be in PZ, PY, or PX, because those orbitals are 90 degrees from each other, and we have bond angles of 109. All right, that is the trouble here. This is the problem that we have to solve. What orbitals hold these bonding electrons? Because they can't be the atomic orbitals that we know. They have to be something else. All right? The answer, the short answer is, there are new hybrid orbitals that are involved in bonding. And that's where this idea of hybridization comes from. All right, now let's take a deeper look. All right, so that was the question that chemists and physicists were trying to answer. And here is the answer that they came up with. Now, first, let's remember what an orbital is. An orbital is something called a probability density function. These are called PDFs, but not the Adobe kind. It's a probability density function. It's a solution to a calculation of the probability of finding the electron. All right, it is a three-dimensional solution telling you where it is most likely to find an electron. All right, it's a three-dimensional solution to a calculation telling you where it's most likely to find the electron. So what they did, what the chemists and the physicists who were trying to answer this problem of what orbitals are holding these bonding electrons, because we're observing these bond angles in nature that are not 90 degrees, where do those come from a first principles perspective? Can we explain that? What they did is they're like, well, what are these orbitals? These are solutions to mathematical equations. Let's do some math on these things. Let's take an average. All right. And I'm going to represent some very sophisticated mathematics, some three-dimensional calculus with a very kind of pictorial representation. But what they did is they took those functions for the orbital and they took an average. They took the s orbital, solutions for the s orbital, plus the solutions for those three p orbitals, and they averaged them together, right? With an average, you sum them all together and then chop them up. We took four things, you add four things together, divide by 4, right? Chop them up into 4 parts. So they took these, the orbitals that carbon had, right? The 1s orbital and the 3p orbitals together, and took an average of them and recalculated these shapes, these probabilities of finding the electron. And what they did is they came up with a new type of orbital. This orbital, the solution to this averaging process, these orbitals have, some characteristic of the s orbital and some of the p orbital. They still have 2 lobes, like the p orbitals that were used to calculate them, but one of the lobes is much larger than the other, because the s orbital is just one big ball. And they got, when they averaged the 2s orbital with 2p orbitals, they got 3 new types of orbitals out. And these were called, they took 4 orbitals in, got 4 orbitals out. These were called sp3 hybrid orbitals. All right, they were, because the kind of the recipe, so to speak, to make these orbitals was 3/4 p and 1/4 s. We say that they have 75% what's called p character, p character, and because 25% came from the s, we say they have 25% s character. Yeah, it's super cool, actually. So these orbitals are kind of hybrids. They're mutant hybrids that are a combination of the components that were used to make them, the s and the p orbitals. Now, here's where things got interesting. When the physicists who did this calculation plotted them in 3-dimensional space, all right, when they actually made a graph of the 3-dimensional shape of these orbitals. Oh, here, hang on one second. You dudes, I'm in class. Quinn, I'm in class, so you gotta whisper. I apologize for that. Exclamation. My kids would normally, well, they're always here, but they're normally quarantined doing schoolwork. Today's Thanksgiving break, and they're in, well, one's elementary school, one's middle school, so they get the whole week off, unlike us. Okay, so let's talk about what happens, or what happened when they plotted those orbitals in three-dimensional space. Let's see, Y and X. Turns out that one of the sp3 hybrid orbitals was oriented directly along the z-axis. A second was in the zy plane. All right. A third was kind of down, but coming out, not oriented along the x-axis per se, but kind of wedged out like so. And then the last one was going down and back. I'm just going to move this guy over just a little bit. And when they measured, okay, what angles exist between these orbitals, these sp3 hybrid orbitals that they calculated, the measured bond angles were 109 degrees, exactly like we see predicted in the VSEPR models. So the answer to the question, remember the question we were asking with hybridization, is what orbitals are involved in forming these bonds? The answer is they're not the atomic orbitals, they're not the s orbital and the p orbitals that we learned. They're these sp3 hybrid orbitals are involved in the bonding of this tetrahedral methane. All right. These sp3 hybrid orbitals, oops, hybrid, not hybrid, are responsible for the bonding we see in this molecule. All right, now, so that's kind of an introduction to what is hybridization, where does it come from, what questions are, those are the, that was the question that we were trying to answer as a scientific community that led to the development of this theory. Now that we have seen it, I want to stop for a minute and talk about bonding. We haven't really talked about bonding. We've been drawing bonds in Lewis structures and three-dimensional VSEPR geometries, but we haven't talked about how those bonds form, other than in Lewis theory, we talked about, oh, the electrons are shared, and that's how those bonds form. But now that we have started this conversation of hybridization, we can actually talk about where these bonds come from and how they form. All right, because again, we said the whole point of hybridization was coming up with an explanation of what orbitals are involved in bonding. So it's high time we talked about what bonding actually is. All right. So Kate, great question. So Kate just asked, is the electron configuration for carbon assuming that there is no hybridization? And the answer to that question is yes. Those are the electron configurations tell you the orbitals that the electrons are in. If you have an isolated atom that is not bonded to anything. So if you have just a sample, for example, of like copper atoms that are just sitting there, which is what we call copper, right? A lump of copper metal. Those copper atoms will have, their electrons will be in atomic orbitals. Those orbitals, the s orbitals, p orbitals, d orbitals, those are called atomic orbitals because those are the orbitals that hold electrons when you just have atoms by themselves. Whenever they're in molecules, those atomic orbitals rehybridize into new hybrid orbitals that are used for bonding. All right, so that is, Kate, exactly correct. When you have an atom, the electrons will be in orbitals defined by the electron configuration. When that atom starts bonding with other things to make molecules, hybridization changes all of those orbitals involved, or changes the orbitals involved. Not necessarily all of them, as we'll see when we get to sp2 hybridization. So let's talk for a little bit about how bonds are formed. Bonds are formed, not formed, through a phenomenon called orbital overlap. Actually, I've got to redo that. I should say that bonds are formed through what's known as constructive. Oops. Okay. Constructive orbital overlap. All right, and what is constructive orbital overlap? It's when you have the orbitals of two molecules. So for example, let's look very simply at hydrogen, whose electron configuration is 1s1, right? It's got one electron in its s orbital. When you form a molecule of H2, what happens is you have one hydrogen. It's got one electron in its 1s orbital. And then you have a second hydrogen that also, actually I'm going to pick a different color. Let's go with blue. That has one electron in its 1s orbital. Now these two atoms move close enough together so that the orbital of one overlaps with the orbital of the other. All right, it may be ugly, but I'm going to live with it. And when they do, when those orbitals overlap, you have two electrons in the space where the one orbital used to be. Now the green hydrogen, the hydrogen with the green s orbital, has access to both its electron and the blue hydrogen's electron. The blue hydrogen now has access to both its electron and the green hydrogen's electron. So they've satisfied the octet rule because they're sharing. They've literally put those two orbitals in the same space. They've overlapped them so that each nucleus has access to both electrons, okay? And that is what we're talking about when we're talking about constructive orbital overlap. And what happens when you get that constructive orbital overlap is a bond forms. All right? Oops. A bond forms. That is how a bond forms. Those two orbitals overlap, and now those two electrons are being shared, and each hydrogen has access to both at the same time. This is the constructive orbital overlap. That is how the bonds form. All right. So let's take this idea of constructive orbital overlap and apply it to the molecule of CH4, which, as we know, is sp3 hybridized. All right. So let's take a look. So I'm going to start by drawing carbon with its 4 hybrid orbitals, 1 electron in each one. Oh, that came out kind of big. All right, there's carbon. Now, we know that carbon has 4 single bonds in this molecule, right? 4 single bonds. And what happens is hydrogen, now hydrogen's orbitals never hybridize. Hydrogen always has 1 electron in a 1s orbital. That is always how it rolls. It comes in and it overlaps its 1s orbital with the sp3 hybrid orbital that carbon has, and that constructive orbital overlap makes the carbon-hydrogen single bond. All right? Now this happens, scoot this down just a little bit. This happens 3 more times, because for each sp3 hybrid orbital, a hydrogen comes in to form a sigma bond, or a single bond. All right, so 1 happens here, 1 happens here. And each time you get that constructive orbital overlap, you get a new bond between carbon and hydrogen. All right? Now, I want to spend a minute to talk about the type of bond that has been formed. Up to this point in time, we've been calling these single bonds. All right? And that's fine as a name, it's not the formal name for this type of bond. One single bond is called a sigma bond. All right, so here you form one single bond. Oops. Hang on. There we go. And the name for that one single bond is, this is called one sigma bond. All right, and that will be important for the future. All right. What makes a sigma bond in a sigma bond, two electrons are held between two nuclei. Because of this, because you have the two negative electrons sandwiched in between two nuclei, which are just balls of positive charge, right? That is where they're going to be the most stable, because it's negative sandwiched in between two positives. So because of this, sigma bonds are more stable in other words, lower in energy. Than pi bonds. All right. What is this enigmatic pi bond? You might ask, what is this new type of bond? You'll have to wait till Wednesday to find out. The answer to that question lies in where this lecture is headed in our discussion of sp2 hybridization. But I'm looking at the clock, and I don't believe we have time to wrap that up, or if we do, it'd be rushed, and I'd rather take our time with this because this stuff is important. So we're going to go ahead and put a pin in lecture there. We'll resume Wednesday with a discussion of sp2 hybridization and pi bonds. So if I don't forget, we got office hours tonight. If I don't see you tonight, I will catch you in lecture on Wednesday. Later, dudes.